In this video, I want to discuss how we can analyze analytically recursive methods. So up until now, all the methods that we've seen have conveniently enough not been recursive. So basically all the code there is just in that one code block, right? All the lines are there. And I'm not really calling any functions at all, right? I'm not calling functions at all. I'm also not calling myself. I'm calling myself, right? Making something recursive is really where we get an issue. We've kind of just been avoiding this for the sake of simplicity. Now, of course, we're going to have plenty of real-world functions that are recursive, and we're going to need a way to analyze them. The issue is that they can become very difficult to understand. So given a function, right, and we can say maybe we have something like, for example, binary search, right? We've seen binary search in terms of kind of the iterative solution that uses a loop. There's also another version of it that's recursive. Basically, every time you divide your domain in half, right, and you go looking for something, you make another recursive call. Those functions are pretty common, right, that are recursive. Well, for a function like that, one thing we could hope to do is maybe write a growth function that could at least represent how many operations it'll take. And generally what these are things are called a recurrence, because you'll have your f of n basically on both sides. So I'll suppose for a second, I don't know if this is 100% right, but let's say for binary search, the recurrence may look something like this. F of n equal f of n over 2 plus 1. Right? So if I'm running binary search on a particular input of size n, the amount of work it needs to do, right, the number of operations, number of comparisons it needs to do, is the number of comparisons to do binary search on 1/2, right, because and the mechanism of the algorithm is right, it's only going to look on 1/2, plus 1, right, because you need to basically compare that current element and decide, is it what I want, or do I go left, or do I go right? So the growth function for something like binary search, binary search, let's just say binary S, okay, is f of n equal f of n divided by 2 plus 1. We'll suppose that. I think I might be off by 1 or 2, but that's okay. Point is, this is a little bit different than what we've seen before, because our growth function that we would write for a recursive method is actually now referring to itself, right? It's a recurrence. So we have f of n on both sides. And so it's not always that bad to write them. But what is bad is to solve them, because this by itself, right, is it's a recursive mathematical formula, and what we really want is a closed loop solution to it, right, or a closed loop form of it, and that takes some work to get, and we'll talk about that a little bit. Really, though, it's something that's out of the scope of this class. So I guess just to expound on that, for this class, for SER222, my expectation is that you can look at a recursive function and kind of understand what are the implications on algorithm analysis. I may be able to write a growth function for the recursive function, but what I'm not expecting you to do is to be able to actually go through the process of deducing the growth function for it and then getting the closed loop for it, right? So you should be able to answer questions about it, you should be able to understand it, but don't expect to actually be asked to do something. Don't expect to actually be asked to find a closed loop formula solution, right? It's a little bit more complicated than what we're doing in this class in terms of the math work behind the scenes. So the way we're going to introduce this whole thing is we're going to actually go step by step through an example of analyzing an algorithm that solves the towers of Hanoi problem. So let's go ahead and move to that.